What if the stuff you call solid was never a substance at all? Pick up your phone. Feel its weight. Tap the glass. It seems obvious. This object is made of something, layers of matter stacked into certainty. But the deeper we chase that something, the stranger the hunt becomes. Atoms once looked like the final bricks of reality, until we split them. Protons and neutrons looked fundamental until they fractured into quarks. Even quarks, in our best descriptions, behave less like tiny beads and more like fleeting events, excitations that appear, interact, and vanish. So here's the pivot. Maybe the question, what is it made of, is already smuggling in the wrong assumption that reality must be built from smaller and smaller chunks of stuff. Modern physics keeps whispering a different story. What we call matter may be nothing more than stable patterns in a deeper web of quantum fields. The way a whirlpool is a recognizable shape in flowing water, not a separate thing inside it. This video follows the trail from ancient atomists to Bohr, Dirac, Higgs, and beyond, not to turn you into a physicist, but to break a habit of mind. Stay with it, and you may never look at a table, your body, or even your sense of self the same way again. Because if matter isn't made of anything, then the real question isn't what the world is made of, but what it's becoming. But here's where things quietly break. When physics first uncovered this strange picture of reality, not everyone agreed on what it meant. In the early 20th century, the equations of quantum mechanics worked flawlessly. They predicted experiments with uncanny precision. Yet when Albert Einstein asked a simple question, what is actually there, when no one is looking, he was told the question itself was misguided. Niels Bohr, one of the architects of quantum theory, insisted that physics should not describe what reality is, only what we can say about it. Einstein refused to accept that, and in that disagreement, something profound surfaced. The possibility that our deepest theories no longer describe stuff at all, only patterns of outcomes. The question, what is it made of, was no longer just difficult. It had become controversial. The habit is already there, long before we name it. A hand reaches out, presses against the world, feels resistance, and quietly decides, there must be something solid underneath all this. Imagine a child with a toy that has stopped working. The first impulse is simple and ruthless. Break it open. Peel away the colored plastic shell. Split it into halves. There must be a secret inside. A spring, a tiny motor, some hidden piece that does the real work. The toy, in that moment, is no longer a friend or a character. It becomes a container, a box holding something more important than itself. That instinct never really leaves, we just give it sharper tools and grander objects. A surgeon opens a chest with careful cuts, looking for the blocked vessel, the damaged tissue. An engineer pulls apart an engine, searching for the worn gear, the cracked seal. A physicist builds machines that slam particles together at unimaginable speeds, hoping that, just for an instant, the pieces inside the pieces will reveal themselves. All of this rests on a quiet conviction. Whatever you see on the surface cannot be the whole story. There is always something smaller, something more basic, something that explains the rest. The bigger thing is only a disguise. The question that guides this search sounds innocent. What is it made of? It seems like the kind of question a curious child would ask about anything. A table, a cloud, a star. It feels like a question that goes straight to the heart of things. Yet buried inside that question is already a decision about what reality must be like. It assumes that the world is built from parts, that those parts are also built from parts, that the chain of ingredients goes downwards in a neat staircase, that there is some final layer of stuff at the bottom. We rarely see how much power language has in this. The way we speak does not just describe the world. It trains us to expect a certain shape from it. Nouns make things look self-contained. Chair, stone, tree, person. Each word wraps a set of experiences into a single package and then pretends the package is a stable thing living out there on its own. Once the noun is in place, the next step follows almost automatically. If there is a chair, then there must be some material that the chair is made of. Wood, metal, plastic. If there is a person, there must be flesh and bone and blood underneath. And if we keep digging, if we ask what wood is made of, what flesh is made of, we expect the answers to keep coming in the same form. Smaller nouns, smaller things, molecules, atoms, nuclei, particles. Language makes this feel obvious. It gives us a grammar that favors objects, containers, and contents. It whispers that behind every appearance, there must be a more real thing. And behind that thing, another. The question, what is it made of, sounds neutral, but it already treats reality as a kind of layered sculpture, with each layer carved from some underlying substance. Even our oldest stories about nature follow this pattern. Long before modern experiment, thinkers imagined the world as built from tiny, indivisible units. They gave them names that meant uncuttable, describing a grain of matter that could not be broken further. This was not an experimental result. It was the natural endpoint of that instinct. If you keep cutting, there must be a last piece that resists the blade. In those early pictures, the world becomes a kind of cosmic mosaic. Big things are arrangements of little things. Change is just rearrangement. Fire, water, earth, air, or a small set of basic atoms moving in the void. The imagination remains the same. There are pieces. The pieces have properties. Combine them in different ways and you get everything else. On the surface, science seems to have honored this vision. At first glance, it looks like a triumphant answer to the old question. What are things made of? They are made of molecules. Those molecules are made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Those are made of quarks. The list of ingredients grows more detailed. The experiments more precise. But the shape of the story looks unchanged. Big things made of small things. Look more closely, though, and the edges start to blur. Each time physics has descended to a deeper level, the new layer has refused to behave like a smaller version of the layer above. Atoms are not little hard balls. Electrons do not orbit like planets. Quarks cannot be isolated and kept in a jar. The more we inspect these supposed building blocks, the less they resemble familiar pieces of stuff, and the more they resemble events, patterns, or ripples in something more abstract. The question, what is it made of, silently demands an answer in terms of things. But the answers we actually find keep drifting away from that demand. They describe fields, probabilities, symmetries, excitations. They give us equations that predict outcomes with astonishing accuracy. Yet those equations do not point to a tiny brick we can hold in our mental hand. They point to structures that do not fit comfortably into the category of substance. This tension reaches past physics into something more personal. We have built our sense of reality around the idea of stable things. Solid objects on a solid stage. If even matter refuses to be made of something in the old sense, what happens to that background feeling of solidity that runs silently through everyday life? What happens to the way we picture our own bodies, or the self we believe is housed inside them? There is a deeper discomfort here. The dream of a final building block offers more than intellectual closure. It promises a kind of existential flaw. If there is a last ingredient, fixed and certain, then somewhere beneath the flux of experience, there is something that simply is, unchanging, reliable. An ultimate answer, even if we never reach it ourselves. To ask what is it made of is also to ask, is there something under all this that does not give way? Modern physics has pushed this dream to its limits. It has given us models in which matter is described as a collection of fields stretching through space. Patterns in those fields appear as the particles we detect. The chair, the hand, the body become configurations of excitations in a web that, as far as we can tell, never settles into a completely motionless, solid form. The notion of a basic chunk of stuff, begins to lose its grip. Yet our language has not caught up. We still talk as if everything around us is a noun first and a process second. We speak as if tables exist the way stones exist in a sculpture garden, calmly waiting, unchanged, between events. We treat the word person as if it pointed to a single thing that persists while experiences flow around it. The grammar of substance and container continues to shape how we notice the world, even when the best descriptions we have contradict it. This is the quiet trap. We inherit a way of speaking and thinking that insists on solid pieces. Then we use that same framework to interpret results from theories that are trying to tell us something stranger. When the theories do not fit easily, we simplify them back into the language of little beads and invisible balls. We draw comforting pictures of electrons orbiting like planets or particles bouncing like billiard balls, because the alternative is harder to hold. Not technically harder, although it can be subtle, but emotionally harder. It asks us to live with a world that is not built the way we were taught to feel it. Perhaps, then, the most radical move is not another experiment, but a small shift in the question itself. Instead of asking what is matter made of, we can ask whether that way of asking even applies. Does it make sense to demand that everything be made from a more basic substance? Or are we forcing the universe to fit an expectation that comes from our grammar, our tools, our hands, more than from the world itself? To explore that, we will stay with physics, but we will not treat it as a collection of final answers. We will treat it as a record of how our questions have evolved. At each stage, the attempt to find the thing inside the thing has led to a new conceptual break. The old picture shattered, a new one reluctantly formed. Along the way, not only our picture of matter changes, but our picture of what it means to exist at all. The aim is not to argue that nothing is real, or that the world is a mere illusion. The aim is quieter. It is to notice how deeply the idea of being made of something has shaped our sense of reality and of ourselves, and then to see what remains when that idea is loosened, if only slightly. History did not loosen that idea with an argument. It loosened it with glass, electric sparks, and a flash in the desert that turned sand into fused stone. For a long time, the atom felt like the natural resting place for the question, what is it made of? Philosophers had imagined something like it long before anyone could test the idea. A smallest unit, uncuttable. The last grain after every possible division. When 19th century chemistry began to show that substances combine in fixed proportions, the dream gained a new kind of confidence. If elements always join in the same simple ratios, it is tempting to believe that matter is literally built out of tiny, repeating units, as regular as bricks in a wall. The laboratory, at first, seemed to agree. Chemists could treat atoms as neat bookkeeping devices. They did not have to picture what an atom looked like inside. It was enough to imagine each atom as a solid bead with a certain mass and a certain kind of charge, bumping into others to form molecules. The world could then be read as a vast choreography of these invisible grains, colliding and sticking according to simple rules. But there was another tradition quietly unfolding in rooms filled with glass vials and faint blue glows. Physicists were experimenting with what happened when an electric current was driven through gas at low pressure, sealed in glass tubes. A glass tube with most of its air removed behaves strangely under high voltage. A pale light appears. Shadows form. A bright patch of fluorescence glows on the glass opposite a metal electrode. These glowing traces were called cathode rays. At first they were just a curiosity, a side effect of tinkering with electricity. Step by careful step, the curiosity became an opening. By bending these rays with electric and magnetic fields, by watching how much they deflected compared to their brightness, experimenters concluded that they were not just light, but streams of charged entities with a very small mass. Eventually, one particular investigator argued that these pieces were far lighter than any known atom, and that they must be a new kind of constituent of matter. Tiny carriers of negative charge, later given the name electron. The atom, once imagined as a smooth, solid grain, now contained something inside it that could be extracted and steered. It was no longer the final bead. It had structure, The picture that followed tried to keep our intuition comfortable. If there are small negative pieces, perhaps they sit inside a positively charged blob, like raisins in a pudding. The metaphors came quickly, yet the world refused to stay that simple. In Manchester, a team led by another physicist began to probe atoms in a more direct way. They used particles emitted naturally by radioactive substances. Small projectiles that carry a positive charge and considerable energy. These projectiles, called alpha particles, were fired at an extremely thin sheet of metal, often gold hammered to a foil, so delicate it was almost transparent. If atoms were diffuse balls of charge, the projectiles should pass through with only small changes in direction, like bullets through a light mist. Most did, but every so often, to the astonishment of the researchers, a projectile bounced almost straight back. It was as if, one of them said later, a cannon shell had been fired at tissue paper and rebounded. To make sense of this, the old picture had to be discarded. The atom could not be a uniform blob. Almost all of its mass and positive charge must be concentrated in a tiny central region, with the electrons somehow arranged around it. That dense core was given a simple name: the nucleus. The rest of the atom, by volume, is almost entirely empty space. That word, nucleus, hides how radical the shift was. What feels like solid matter under your hand is, at this scale, a pattern of electromagnetic attraction and repulsion around a nearly point-like center. If you could enlarge an atom until the nucleus was the size of a small seed, the nearest electrons, according to this picture, would be smeared out somewhere at the distance of a cathedral. Between them, nothing you would recognize as substance, just fields and space. Even this was not the end of the story. The nucleus itself turned out to be composite. Over time, different experiments revealed that it consists of positively charged particles, called protons, and neutral ones, called neutrons. The neutron, in particular, is subtle. Because it carries no electric charge, it can slip much closer to other nuclei than a charged projectile can, making it an ideal probe of nuclear structure. Its identification in the early 1930s transformed the way physicists thought about the interior of atoms. Once neutrons were available as tools, something even more unsettling emerged. When certain heavy nuclei are struck by a neutron, they do not simply jiggle and return to rest. They can split into two smaller nuclei, releasing additional neutrons and a vast amount of energy in the process. This splitting is called nuclear fission. The key is that the new neutrons can, in turn, strike more nuclei and cause further splittings. Under the right conditions, this becomes a chain reaction, a self-sustaining cascade of events in which each step triggers the next. Here the question, what is it made of, turns into something more dangerous. If a small amount of heavy material contains within it the possibility of such a chain reaction, then matter is not just a passive collection of bricks. It is a reservoir of energy, locked in the configuration of its nucleus and waiting, under certain circumstances, to be rearranged violently. This understanding did not stay on paper. During the Second World War, a secret network of laboratories and test sites was assembled to turn nuclear fission into both a weapon and, later, a source of power. In an isolated stretch of desert in the southwest of the United States, a device based on plutonium, a heavy element capable of sustaining a rapid chain reaction, was assembled and placed atop a steel tower. In the early morning of a day in mid-1945, it was detonated. The explosion was the first nuclear test in human history. Sand near the site liquefied and cooled into a pale, glassy material. A mushroom-shaped cloud rose into the sky. Windows rattled many kilometers away. For the first time, the energy bound up in a handful of matter had been released in a form that could erase a city. Within weeks, nuclear bombs were dropped on 2 Japanese cities, one device using uranium, another using plutonium. The first use of such weapons against human populations is part of the historical record, not a theoretical scenario. The images that followed are as much a part of the story of the atom as any diagram of orbits or energy levels. Burned shadows on walls, ruined streets, survivors living with cancers and other long-term effects of radiation, debates, regrets, justifications. None of that can be separated from the question of what it means to break matter apart. At this point, the idea of the atom as a quiet building block of the world has been thoroughly altered. It is no longer an indivisible grain of substance. It is a complex structure with internal components. It is mostly empty. Its nucleus is held together by forces that can, under the right perturbation, release far more energy than chemical reactions ever could. A gram of nuclear fuel, properly arranged, can yield as much usable energy as many tons of coal. That comparison is almost too large to feel, but it is real. Technical language tends to smooth over the strangeness. Words like electron, proton, neutron, nucleus, chain reaction, reactor, and warhead become routine. An electron is often introduced as a tiny, negatively charged particle. But that description hides more than it reveals. In quantum theory, it behaves as a kind of spread-out, wave-like entity whose position is never entirely sharp. A proton is said to be a positively charged particle in the nucleus, but it is itself a bound state of smaller constituents, quarks and gluons, whose restless motion accounts for most of its mass. A neutron, described as a neutral partner to the proton, quietly serves as the key that opens the door to fission when it slips into certain heavy nuclei. The more detailed our picture becomes, the less it resembles the intuitive idea of a simple ingredient. An atom, seen through this lens, is not a small sphere of stuff. It is a pattern of charges and forces, a stable configuration of interactions. Split it, and you do not reveal a smaller lump of the same material. You transform the pattern into new patterns and, if you choose certain paths, release energy that had been locked into those patterns since long before life emerged on this planet. There is an existential edge to this. Human beings reached into the heart of matter looking for understanding and found, along the way, the ability to alter the conditions of life on Earth irreversibly. The same chain reactions that can power cities can also end them. The atom, once a symbol of permanence, became a symbol of fragility, of how easily things we treat as stable can be turned into something else entirely. From glass tubes glowing in darkened rooms to towers of steel in the desert, the pursuit of what is inside the inside has forced us to confront not just the structure of matter, but the weight of acting on that knowledge. Each experimental advance has come with a choice about what to do with the power it grants. And under all of this, the original question quietly shifts. When we shatter atoms and harvest their energy, we are no longer just asking what matter is made of. We are entangled with a different inquiry. What kind of beings choose to work with a world that behaves this way, where the smallest scales carry consequences that reach into politics, ethics, and the survival of entire populations? The atom did not simply surrender its secrets, it traded them for responsibility. Responsibility has a way of pulling us forward, even when every step reveals that what we thought was firm ground is only a temporary arrangement of deeper uncertainties. Once the atom had surrendered its nucleus, it might have been tempting to declare victory. There is the electron, there are the protons and neutrons. There is the strange energy locked in their bonds. The brick has been cracked open and its pieces catalogued. But nature has a habit of answering our satisfaction with more detail than we asked for. To explore the nucleus, you need projectiles far more energetic than the alpha particles used in the earlier gold foil experiments. That demand led to machines whose only job is to push charged particles to enormous speeds and then smash them into targets. These are particle accelerators, long tunnels or circular tracks where electric fields act like repeated shoves, each one adding a little more speed, until the particles move so close to the speed of light that ordinary language starts to lose its grip. When those accelerated particles strike a target, the collisions are not tidy. Instead of one clean fragment, physicists began to see sprays of new particles fan out from the impact, each leaving a curved trail in detectors filled with gas or layered with photographic plates. Those trails recorded how the particles bent in magnetic fields and how they lost energy, giving clues to their charge, mass, and lifetime. Very quickly, the simple story of protons, neutrons, and electrons began to dissolve into a crowded menagerie. New particles kept appearing. Some lived long enough to travel measurable distances before decaying. Others existed only for a fleeting instant and had to be inferred from their decay products. They were given names that hinted at the confusion as much as the physics: pions, kaons, sigmas, lambdas. Collectively, they became known as the particle zoo. A zoo is not just a collection. It is a sign that classification has outrun understanding. Each cage holds an animal. Each animal has a name. But the deeper question of how all these forms relate remains open. In the same way, each new entry in the particle zoo could be described: its charge, its mass, its typical decay channels. But the list itself grew unwieldy. It did not feel like a final answer. It felt like a symptom that some underlying pattern had not yet been seen. The key words here, often taken for granted, also deserve a slower look. A particle, in this context, is not literally a tiny speck of hard matter. It is an entity that, when measured, behaves as if all of its mass and charge are concentrated in a very small region of space. A decay is not a piece crumbling like a clod of dirt, but a process in which one pattern of mass and charge changes into another, in ways constrained by conservation laws. Even the word mass, usually associated with heaviness, is better thought of as a measure of how strongly an object resists changes in its motion. Within this growing chaos, a few physicists began to suspect that the zoo might be hiding a simpler scheme. Instead of treating each hadron as fundamental, they imagined that protons, neutrons, and many of the new particles might be composites, built from even more basic ingredients. The term hadron, in case it sounds opaque, refers to any particle that feels the strong nuclear interaction, the force that binds protons and neutrons in the nucleus. Mesons are hadrons that behave, very roughly, like pairs of more basic constituents, while baryons behave like triplets. The proposed constituents were given a short, strange name: quarks. The word is unusual enough that it resists turning into a comforting image. That is almost an advantage. A quark is not a little ball with hooks or bumps. It is a basic entity in a mathematical model, assigned a certain electric charge, a kind of spin, and a new kind of charge associated with the strong interaction, called color. Color in this context is not about visual hue. It is a bookkeeping label that helps track how quarks combine and how the strong force acts on them. At first, quarks lived mostly on paper. They made sense of the particle zoo by organizing hadrons into families. Patterns that had looked arbitrary suddenly lined up into systematic arrangements. Charges added up neatly. The list of possible combinations explained why certain particles existed and others did not. It was as if a language with many irregular verbs had been rewritten into a more regular grammar. Still, a model that only tidies up the catalog is not enough. For quarks to be taken seriously as more than a clever counting trick, there had to be experimental signs that something like them really existed inside protons and neutrons. Those signs came from another kind of scattering experiment. Instead of using heavy particles as projectiles, physicists fired very energetic electrons at protons. Electrons are useful probes precisely because, as far as current theories go, they show no internal structure. They are as simple as anything we know how to describe. When such an electron scatters off a target, the pattern of its deflection reveals information about how charge and momentum are distributed inside that target. In the late 1960s, experiments at a laboratory on the west coast of the United States used this method to probe the interior of the proton. The results showed that, at very high energies and very small distance scales, the proton does not behave like a smooth, featureless blob of charge. Instead, it responds as if its interior contains several smaller, point-like scatterers carrying portions of the proton's momentum and charge. These scatterers were interpreted as the quarks the theorists had been talking about. The proton, then, emerged not as an indivisible brick, but as a dynamic composite system. Three main quarks, surrounded by a restless sea of quark, antiquark pairs, and gluons. Gluons are the carriers of the strong force, in the same way that photons are the carriers of the electromagnetic interaction. They bind quarks together, and in doing so, they contribute most of the proton's mass. This last point is quietly radical. The mass of a proton is not simply the sum of the masses of its three primary quarks. In fact, the quarks themselves account for only a small part of the total. Most of what we experience as the mass of ordinary matter arises from the energy stored in the motions and interactions of quarks and gluons inside protons and neutrons. The famous relation between energy and mass tells us that energy can show up as mass, and here it does, not as a smooth filling, but as a continuous dance of confined constituents. The classification of quarks settled into a set of types called flavors. There are 6 in the standard description: up, down, strange, charm, bottom, and top. The names are almost playful, a reminder that terminology is a human layer draped over abstract structures. Up and down quarks are the lightest and most common. They are the ones that make up the protons and neutrons in ordinary matter. Strange, charm, bottom, and top are heavier and appear mainly in high-energy processes, quickly decaying into lighter particles. Again, each technical term carries more meaning than the casual listener might guess. Flavor, here, is not taste. It is a label distinguishing different versions of quarks that share some properties but differ in mass and certain interaction strengths. Spin is not literal rotation, but a quantum property that determines how the particle responds to magnetic fields and how it behaves under rotations of the coordinate system. Color is not hue, but a way of making sense of the strong force, whose rules demand that certain combinations of quark colors are allowed while others are forbidden. There is also a crucial property of the strong force called confinement. Quarks, as far as experiments can tell, cannot be isolated as free particles. The force between them does not weaken as they are separated. Stretching a pair of quarks apart eventually pulls so much energy into the field between them that it becomes favorable to create a new quark-antiquark pair, keeping all quarks bound inside hadrons. This is very different from the electromagnetic force, which diminishes with distance and allows individual charged particles to wander freely. Confinement has a subtle philosophical bite. We infer the existence and properties of quarks from the patterns they produce, from the way hadrons scatter and decay, from the success of the theory that uses them as building blocks. Yet we can never, under current understanding, hold a single quark up and say, here it is, isolated. The things we call fundamental are entities that show themselves only through relations and effects, never as self-standing objects in a void. At this stage, the metaphor of a brick starts to feel strained. A brick is a solid volume with a clear boundary. It persists. It can be stacked. Protons and neutrons, seen through the lens of quarks and gluons, are not like that. They are states of a field, patterns of interaction, that maintain a recognizable identity over time, but whose internal contents are in constant flux. If you could somehow freeze a proton, you would still find that its inner landscape is a cloud of possibilities, not a fixed arrangement of tiny marbles. The idea of the particle zoo gives way to a different image, not a collection of unrelated animals, but a set of resonances of a deeper structure. Each hadron becomes a particular way in which quarks and gluons can be arranged, while respecting the symmetries and conservation laws of the strong interaction. Many of the zoo's citizens, once mysterious, are reinterpreted as excited states or combinations in this underlying theory. From the outside, this looks like progress. A Baroque catalogue has been replaced by a more unified scheme. Instead of dozens of independent particles, there is a smaller set of basic fields and rules. Yet the psychological effect is more complicated. We gain a clearer story about how the pieces fit, but the pieces themselves become less like things and more like roles. In a play whose stage is not even fully described, each time physics has descended to a smaller scale, the supposed building blocks have turned out to be structured, dynamic, and in some sense derivative. Atoms depend on nuclei and electrons. Nuclei depend on protons and neutrons. Protons and neutrons depend on quarks and gluons. At each level, The language of substance does less work, and the language of patterns and interactions does more. This raises a quiet question that sits in the background of all these discoveries. If every brick we find is built from smaller bricks that are themselves patterns in fields, is there a final layer where the metaphor of being made of something still applies? Or is the very idea of a basic thing slowly dissolving? The journey from the particle zoo to quarks suggests that what we call a fundamental object may just be where our current theories decide to stop, not where the universe actually bottoms out. The idea of a final brick dissolves more completely when we stop looking for pieces at all and start paying attention to something that does not look like a thing. Long before quarks, before particle accelerators, people were already playing with invisible influences they could not see but could feel. Rub a piece of amber on cloth, and it attracts bits of straw. Bring a magnet near iron filings, and they rearrange themselves into delicate patterns. A storm gathers in the sky and suddenly releases a flash of lightning between cloud and ground. In each case, something seems to reach across empty space. For a long time, these effects were described in terms of forces that acted at a distance. A charged object pulls on another charged object. A magnet attracts a piece of iron. Gravity pulls apples down and keeps planets in orbit. The language suggests direct, immediate connections between separated bodies, as if they simply know about each other without anything in between. A different way of thinking emerged when a certain experimenter began to picture space itself as filled with structure. He drew lines around magnets to represent how a small test magnet would point if placed here or there. He spoke of lines of force, as if the space around an object were organized, not neutral. These lines were not literal threads. They were a way to visualize a field. In physics, a field is a simple but powerful idea. It is a quantity defined at every point in space and time. For a temperature field, you can imagine that every location in a room has a particular temperature assigned to it. For an electric field, every point in space has a certain push or pull that a charged particle would feel if it were placed there. The field is not another object sitting in space. It is a description of how space itself is structured in terms of the potential to influence something. This shift from forces between objects to fields in space was more than a change of taste. Once you think in terms of fields, electricity and magnetism stop being separate chapters. Experiments showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. A spark in a coil of wire can induce a current in another coil some distance away, not by chunks of matter flying between them, but by a disturbance in the electromagnetic field connecting them. A Scottish theorist took these fragments and wrote down a set of equations that captured this interplay. The details of the mathematics are not needed here. What matters is what those equations said. They described electric and magnetic fields as two aspects of a single entity, the electromagnetic field, and they predicted that this field can support waves that travel through space. A wave, in this context, is a repeating pattern of variation that moves. For a water wave, the height of the water rises and falls as the wave passes by. For an electromagnetic wave, the strengths of the electric and magnetic fields rise and fall, pushing and twisting in a coordinated way. The equations showed that these waves travel at a specific speed. When that speed was compared with measurements done on light, the match was extraordinary. The conclusion was hard to avoid. Light is a wave in the electromagnetic field. This is a quiet revolution. Light, which had been treated as a stream of particles or a kind of ethereal substance, becomes a self-sustaining ripple in a field that fills all of space. There is no need for a hidden medium. The field itself is the medium. What you see as brightness is the effect of this oscillating field on the charged particles in your eyes. The practical reality of fields became harder to ignore when experiments moved from sparks on the bench to signals sent through the air. In a laboratory at the end of the 19th century, an experimenter generated sudden changes in electric current in a circuit and detected disturbances appearing in a loop of wire across the room. These disturbances behaved just like light. They reflected, refracted, and interfered. They were electromagnetic waves with longer wavelengths. eventually used for radio. If you hold a phone or sit near a wireless router, your body is being crossed constantly by electromagnetic waves of various frequencies. Frequency, here, means how many crest and trough cycles pass a point in a given time. Wavelength means the distance between two successive crests. Different frequencies and wavelengths correspond to different kinds of electromagnetic radiation. Radio, microwaves, visible light, ultraviolet, X-rays, gamma rays. The words sound exotic, but they are all just different ways the same field can vibrate. Notice what has happened. Instead of thinking of empty space dotted with particles that exert forces on each other, we now think of space as filled with fields that can store and transmit energy. Objects are places where fields are particularly intense or organized. The background is no longer nothing. It is an active participant. Yet the story did not settle there. The wave picture of light, beautiful as it was, ran into puzzles. One famous puzzle involved what happens when light shines on certain metals. If you illuminate a metal surface with light of low frequency, no matter how bright, electrons do not escape. Increase the frequency beyond a certain threshold, even with weak light, and electrons pop out with a noticeable kick. This is the photoelectric effect. The name simply means that light, or photons as we now say, cause electricity to flow. But at the time, the details did not make sense in a pure wave picture. A wave spreads its energy out. If brightness is simply more intense waving, then very bright low-frequency light ought to be able to push electrons out eventually. It does not. A bold proposal solved this. Light, though described as a wave in the electromagnetic field, sometimes behaves as if it delivers its energy in discrete packets. Each packet carries an amount of energy proportional to the frequency of the light. If the packet energy is below a certain threshold, no single packet has enough to pry an electron free, no matter how many packets arrive. Once the frequency is high enough, each packet carries enough energy and electrons are emitted. These packets came to be called photons. A photon is not a tiny billiard ball. It is a quantum of the electromagnetic field, the smallest indivisible bundle in which the field can exchange energy with matter in a given mode of vibration. In experiments, light sometimes insists on this particle-like face, even though the underlying description still uses a field that can form waves. We are pushed into an uncomfortable compromise. In some situations, light behaves like a continuous wave spread over space. In others, it behaves like a collection of localized quanta. The same dual character appears for electrons and other entities we used to treat as particles. Toss electrons at a barrier with two narrow slits, and a pattern of alternating bright and dark bands appears on a screen. Just like light through two slits. That pattern is the hallmark of waves interfering with each other. Yet the screen records impacts in separate spots, as if individual particles had arrived. This is not a matter of our instruments being crude. The experiments have been refined repeatedly. Send the electrons one at a time, and the interference pattern still builds up, dot by dot. The world does not cooperate with our desire to classify its ingredients once and for all as either things or waves. Fields offer a way to hold these contradictions more steadily. Instead of starting with particles and adding mysterious wave behavior, we start with fields defined everywhere, and then treat particles as particular excitations of those fields. An excitation is simply a disturbance that stands out from the background. For the electromagnetic field, certain stable, localized disturbances behave in experiments like photons. For the electron field, localized excitations behave like electrons. This does not fix all puzzles. It does something more modest. It shifts our basic picture. The primary entities are no longer solid lumps. They are fields, and their patterns of excitation. What we call a particle is a way a field appears under certain conditions, especially when we measure it with instruments that register discrete events. Some of the terminology here can sound distant. Electromagnetic means related to electric and magnetic phenomena, which includes everything from the push between charged particles to the attraction between a magnet and a piece of iron to the light striking your eye from a screen. A field, as before, is a mapping from each point in space and time to some values such as electric strength and direction. Wavelength is the spatial period of a wave. Frequency is how often the pattern repeats in time. None of this requires mystical interpretation. It is simply a language for making sense of the regularities we observe. Yet the conceptual cost is real. If fields fill all of space, and particles are just ways those fields vibrate, then there is no clean separation between something and nothing. The vacuum, in this view, is not the absence of everything. It is the lowest energy state of the fields, still able to support fluctuations and temporary excitations. Later theories would make this picture even more explicit. But the seeds are already here. This reaches back into how we live with the world. We are used to thinking of ourselves as bodies moving through emptiness, occasionally interacting with other bodies. In a field description, this is almost turned inside out. The space between you and the chair is not a blank gap. It is a region where electromagnetic and gravitational fields, among others, are present and active. The resistance you feel when you sit is the result of interactions between the fields associated with the atoms in your body and those in the chair. Nothing literally collides in the old sense. Fields respond to fields. Once fields step into the spotlight, the question, what is it made of, starts to look different. Ask what light is made of, and the answer leads to the electromagnetic field and its quanta. Ask what a radio wave is made of, and you get the same answer, just with a different frequency. Ask what holds a magnet to a refrigerator door, and the answer again is expressed in terms of fields and their energy. The object we began with, the magnet, becomes a region where certain field configurations are especially strong and ordered. We are no longer peeling layers off a solid onion, hoping to reach the core. We are mapping a network of fields, watching how they influence each other, and learning that many of the distinctions our language likes to draw between object and space, between thing and nothing, are less clear at this level than they feel in daily life. The next steps in physics would push this even further, combining the field idea with quantum rules into a framework where every known particle is a field excitation. Before that, though, the simple atom, with its electrons and nucleus, had to be rewritten once more. Fields were waiting, not only in the space around matter, but inside the structures we had thought were already explained. The same tools that let us draw fields in the space around matter eventually forced us to redraw the space inside matter itself, until even the idea of an inside began to slip. After the nucleus entered the picture, it was natural to think of the atom as a tiny solar system. A small, heavy center. Lighter pieces, the electrons, circling around it like planets around a star. The picture is satisfying. It uses a structure we already know. It lets us imagine electrons as marbles in motion, tracing stable paths. Classical physics, though, is not kind to that image. In ordinary electromagnetism, a charged object that moves in a circle is constantly changing direction. A change in motion is an acceleration, even if the speed stays the same. Accelerated charges radiate energy as electromagnetic waves. If an electron really orbited the nucleus the way a planet orbits the sun, it would emit radiation continuously, lose energy, spiral inward, and crash. By those rules, atoms should be unstable. The matter making up your body should not hold together for even a moment. Yet matter is stable. The world around you does not dissolve into a flash of light. There is a mismatch between the classical picture and the fact that ordinary objects persist. One of the first attempts to repair this contradiction came with a simple but radical suggestion. Perhaps electrons are allowed only certain orbits. Not every path is possible. Only those with specific energies exist. In those privileged orbits, the electron does not radiate, even though by classical reasoning it should. Radiation happens only when the electron jumps from one allowed orbit to another, emitting or absorbing a packet of light whose energy matches the difference between the two orbits. This is the essence of the Bohr model, named after the physicist who proposed it in the early years of the 20th century. It is a compromise. The atom is still pictured as a kind of miniature solar system, but with special rules pasted on top. Quantization. The idea that energy comes in discrete steps rather than a smooth range is introduced as a law. Electrons can stand only on particular rungs of an invisible ladder around the nucleus. The model gains credibility because it explains something long observed but poorly understood: the line spectra of elements. When a gas is heated or excited, it glows past that light through a prism. And instead of a continuous rainbow, you see a pattern of sharp lines at specific colors. Each element has its own pattern. Hydrogen has one, helium another, sodium another. Those lines are not arbitrary. They correspond to photons emitted when electrons fall from higher energy levels to lower ones. The spacing of the lines reflects the spacing of the allowed levels. Quantized orbits make sense of this pattern. Each jump between levels produces light of a definite color. Because only certain jumps are possible, only certain colors appear. The atom acquires a kind of fingerprint, written not in ink but in the allowed transitions of its electrons. Still, something in the picture remains uneasy. The notion of an electron as a little planet that sometimes teleports between orbits without passing through the space in between feels like a temporary fix, not a final understanding. The rules work, but they are stapled onto an image that does not welcome them. A deeper shift begins when matter itself is treated in the same way light had been, as something that can show wave-like behavior. A young physicist suggested that particles such as electrons might have wavelengths associated with their motion, just as light waves have frequencies and wavelengths. The shorter the wavelength, the higher the momentum of the particle. If that is so, then an electron bound in an atom is not simply circling like a marble. It is more like a wave wrapped around the nucleus. A wave that wraps around and joins onto itself must satisfy a simple condition. It must fit an integer number of wavelengths along the allowed path, or else it will interfere destructively with itself. That condition naturally picks out discrete orbits. Instead of quantization being an extra rule, it becomes a consequence of treating the electron as a wave. Only those paths where the electron wave lines up with itself are stable. This idea leads into a more abstract description. Instead of talking in terms of orbits and paths, one writes an equation for a wave function. The wave function is a mathematical object that assigns to every point in space and time a complex number that encodes the amplitudes of different possibilities. When you square its magnitude, you get something that can be interpreted as a probability density. In plain language, the wave function tells you how likely it is to find the electron in a given region if you look. The equation that governs the wave function, introduced by Schrödinger in the 1920s, looks, on the surface, like a wave equation for a vibrating string or a drum skin. But its solutions describe clouds of probability rather than literal motion of a medium. For the hydrogen atom, the simplest real atom, the solutions produce shapes in space where the electron is more likely to be detected. These shapes are what we call orbitals. They are not paths. They are regions of heightened probability. In this view, the electron in an atom is not a little bead whirling in a neat circle. It is a diffuse presence, spread out, with different chance densities in different zones around the nucleus. When a measurement is made, you detect the electron at a particular place. Between measurements, the wave function evolves smoothly according to the equation. The jump from spread-out probability to sharp detection is one of the core puzzles of quantum theory. This picture comes with a principle that limits how sharply certain pairs of properties can be known at the same time. Position and momentum, for instance, cannot both be specified with unlimited precision. The more tightly you know where an electron is, the less definite its momentum becomes, and vice versa. This is the uncertainty principle. It is not a statement about the clumsiness of instruments. It is a statement about the structure of the theory itself. At the atomic scale, the idea that a particle has an exact position and an exact velocity at every instant simply does not fit. For the atom, this means that the older image of electrons as small planets following exact orbits must be abandoned, not just modified. There is no hidden curve in space that the electron traces. There is a pattern of probability, and that pattern is as real in the theory, as any trajectory used to be in classical mechanics. The electron does not have a location in the classical sense until an interaction forces that property to become definite. As quantum theory matured, more features of the electron arose that refused any simple mechanical model. One of them is spin. The word suggests a small sphere rotating about its axis, like a spinning top. That analogy is misleading. Spin in quantum mechanics is an intrinsic form of angular momentum. It describes how the wave function behaves under rotations, and it comes only in discrete values. For the electron, there are two allowed spin states, often labeled spin up and spin down. Spin has concrete effects. It interacts with magnetic fields. It leads to a splitting of spectral lines when atoms are placed in strong magnetic fields, a phenomenon called the Zeeman effect. It also plays a crucial role in the way electrons arrange themselves in atoms and solids, through a principle that forbids two electrons from occupying the same quantum state. That principle, together with spin, explains the structure of the periodic table and much of chemistry. None of this can be captured by imagining a classical little ball literally spinning. The classical picture fails both quantitatively and conceptually. When quantum ideas were blended with the demands of special relativity, which governs objects moving at speeds close to that of light, another layer of strangeness appeared. The equation written down to describe an electron in this combined framework did more than expected. It recovered the known properties of the electron and its spin, but it also suggested the existence of a partner, a particle with the same mass as the electron, but opposite electric charge. This partner, later observed in cosmic ray tracks, is the positron, the anti-electron. Antimatter sounds dramatic, but in this context, it is an unavoidable consequence of marrying quantum rules with relativistic symmetry. For every particle with certain properties, the theory tends to allow a corresponding antiparticle with mirrored charge. When a particle meets its antiparticle, they can annihilate, converting their mass into energy in the form of photons. Again, the atom becomes less and less like a tiny mechanical model and more like a node in a web of possible transformations, with identity contingent on the interactions taking place. Even when an atom seemed well described, tiny effects kept nudging theorists toward deeper revisions. Precise measurements of hydrogen revealed subtle splittings and shifts in its energy levels that simpler models could not account for. One such shift, observed as a small difference between two levels that earlier theory had predicted to be exactly the same, forced the development of a more refined framework. Quantum electrodynamics, a theory in which the electron field and the electromagnetic field are both treated quantum mechanically, and their interactions include contributions from fleeting virtual processes. These corrections are not small only numerically, they are conceptually loud. They show that even the simplest atom is influenced by fluctuations in what we would naively call empty space, and by the possibility of particles briefly appearing and disappearing as allowed by quantum uncertainty. The atom is not a self-contained object sitting in a placid vacuum. It is immersed in, and partly defined by, a restless background of fields. At each stage, the atom has resisted the images offered to tame it. First a hard grain, then a miniature solar system, then a set of quantized orbits, then a cloud of probability, then a pattern in interacting fields with virtual excitations. The equations become more accurate. The predictions match experiments to a remarkable degree. But the intuitive picture grows less and less like anything we evolve to grasp with our senses. There is a quiet, existential cost to following this path. The familiar anchors drop away. Solidity turns into interaction. Location turns into probability. Identity turns into a record of possible transitions. Even stability is reinterpreted as a delicate balance of opposing tendencies, a standing wave in a complex medium rather than a lump resting on a shelf. And yet, the world of tables, stones, and bodies does not vanish. The chair under you continues to hold. The atoms in your bones remain bound. The quantum atom is not here to erase the everyday, but to remind us that the way we carve reality into things is, at best, an approximation that works at certain scales. Below those scales, the questions we ask, such as what is it made of, stop having simple answers. The atom becomes less an object and more a story our best theories tell about how fields arrange themselves into patterns that endure long enough to be called matter. The closer we look for things, the more we find rules and patterns instead. As if reality keeps offering us behavior where we expected substance. Quantum theory, on its own, already replaced the orbiting electrons of the old atom with wave functions and probabilities. But there was still a split in the story. Light and other forms of radiation were described as fields, sometimes acting like waves, sometimes like quanta. Matter, in many treatments, was still spoken of as if it were made of particles first, with quantum behavior added as an afterthought. That division does not last. Once we ask how light and electrons interact in detail, the old separation between fields and particles begins to blur. A theory of this interaction has to describe how an electron emits or absorbs a photon, how two electrons repel each other, how atoms radiate light and absorb it again. Early attempts used particles exchanging forces, with fields as a supporting idea, but the calculations misbehaved. Certain quantities wanted to become infinite. Straightforward methods broke down. The breakthrough came when physicists took a more radical step. Instead of treating matter as made of particles placed into fields, they treated both matter and radiation as fields from the start, and then applied quantum rules to the fields themselves. Every kind of particle we observe would be understood as a possible excited state, or ripple, of some underlying field. The name given to this approach is quantum field theory. A field here is not a poetic term. It is a very specific mathematical object, something that assigns values to every point in space and time, and evolves according to equations that respect relativity and quantum principles. There is an electromagnetic field. There is an electron field. There are fields associated with quarks, with gluons, with neutrinos. Each field is, in the theory, spread out everywhere, even in regions where its excitations are rare. The simplest way to hold this in mind is to imagine a surface that can vibrate in different ways. A stretched string supports many possible patterns of vibration. You can pluck it gently and get a simple tone, or excite more complicated patterns with several peaks along its length. Each pattern corresponds to a certain frequency and energy. In quantum field theory, something similar happens, but in a more abstract space. The field can vibrate in different modes, and when one particular mode is excited in a localized way, the theory describes this as a particle. Think of a grid laid over space, with a tiny spring at every crossing. The field value at that point is like how far the spring is stretched. If all the springs are at their resting positions, the field is in its lowest energy state. It's vacuum. If, in one region, a cluster of springs is set into a coordinated oscillation, that region holds energy. In the quantum description, that localized, minimal bundle of oscillation is a single particle. More energy in that same pattern corresponds to more particles of that type. This is an analogy, not a literal picture, but it points at a crucial shift. A particle is no longer an independent little bead wandering through empty space. It is a particular, smallest possible packet of excitation of a field that is already present everywhere. The field is the enduring entity. The particle is one of its transient, countable disturbances. This way of thinking resolves some of the earlier tensions. When an electron emits a photon, we no longer imagine a small pellet throwing off another pellet. Instead, the electron field and the electromagnetic field interact. A certain pattern of excitation in the electron field changes, and a new excitation appears in the electromagnetic field. The conservation of energy, momentum, and charge is enforced by the structure of the fields and the form of their equations. The interaction is not a collision of things, but a reshaping of ripples in a coupled system. In quantum field theory, even the idea of empty space has to be rewritten. The vacuum is not the absence of all fields. The fields are always there. What changes is their state of excitation. The true vacuum is the lowest energy configuration of all fields combined. But because of quantum uncertainty, those fields cannot be perfectly flat and still. there is always some residual fuzziness. Fluctuations briefly appear and disappear. Small ripples that never travel far or live long, but nonetheless leave measurable traces. These flickers are often described in terms of virtual particles. The word virtual can be misleading. It does not mean imaginary in the sense of fictional. It means that these excitations do not live long enough or travel far enough to be detected as ordinary particles. They exist as intermediate states in processes calculated by the theory. An electron in an atom, for instance, is continually interacting with the electromagnetic field, emitting and reabsorbing virtual photons. These processes, taken together, shift the energy levels of the atom by tiny but detectable amounts. When the predictions of quantum electrodynamics, the branch of quantum field theory dealing with electrons and photons, were compared to experiments, the agreement was astonishingly precise. Subtle details of atomic spectra, corrections to the magnetic properties of the electron, and other quantities, all lined up with measured values to many decimal places. The price of this success was an abstract, counterintuitive picture of reality. Solid-looking objects now emerged as patterns in fields, and fields themselves came with unavoidable fluctuations that could never be turned off. Some terms in this story are so common in popular science that they can slide by without clarity. A quantum is the smallest indivisible unit in which a particular kind of physical quantity can be exchanged. For a field, it is the minimum packet of excitation that can be added or removed in a given mode. A vacuum fluctuation is a temporary change in the energy of a field in a region of space, allowed by the uncertainty principle as long as it happens fast enough. A virtual particle is a way of talking about the influence of such fluctuations on observable processes. The temptation is to imagine all of this as a kind of seething foam of tiny objects popping in and out of existence. But that picture is already a step back toward particles as primary. The more faithful description keeps the fields in front. The fields are what there is. The language of particles, real and virtual, is a way of organizing the mathematics in terms of discrete excitations, especially useful when we talk about what detectors record. From this vantage, the everyday notion of matter being made of particles is both right and incomplete. It is right in the sense that, in many settings, we can treat localized excitations as if they were small, enduring objects that move, collide, and bind. It is incomplete because those excitations are not little bits of substance in a void. They are manifestations of underlying fields. Asking what an electron is made of, in this context, is like asking what a small ripple on a pond is made of. It is made of the pond, arranged in that particular pattern of movement. The analogy with ripples has to be used carefully. A water wave moves on a substance we can see and touch. A field is not a material sheet stretched across space. It is a more abstract entity, defined by how it influences other fields and the outcomes of experiments. When we say an electron is a ripple in the electron field, we are making a claim about how all known phenomena involving electrons can be described consistently, not about a hidden medium that fills the universe like a fluid. Quantum fields also change how we think about forces. In Newtonian terms, a force is a push or pull that changes the motion of an object. In field language, interactions between fields replace that picture. The electromagnetic interaction, for instance, is described as the exchange of photons between charged excitations of the electron field. The strong interaction, which binds quarks inside protons and neutrons, is described in terms of gluons exchanged between quark fields. These exchange particles are themselves quanta of fields associated with the forces. Again, it is easy to slip back into imagining little balls flying between other little balls, carrying pushes and pulls. A more consistent view keeps in mind that what is really being described is the way fields affect each other's patterns of excitation. The exchange particle language is a convenient shorthand for particular structures in the equations. When we apply this picture to something as mundane as sitting on a chair, the result is quietly disturbing. At the microscopic level, the atoms in your body and the atoms in the chair never quite touch. The electrons, which are excitations of the electron field, are arranged in energy levels around atomic nuclei. When you press your hand against the table or lower yourself onto the seat, the electron clouds in your body and those in the chair overlap. The electromagnetic field responds. The patterns of excitation change in such a way that further compression is resisted. You feel that resistance as solidity. No two pieces of matter are actually bumping in the old mechanical sense. Fields are avoiding configurations of higher energy and settling into a compromise. What you experience as a solid surface is the macroscopic expression of these underlying field interactions. The phrase "made of wood" or "made of metal" is not wrong at the human scale. But the deeper story is about electron fields, quark fields, gluon fields, and electromagnetic fields arranging themselves into a stable pattern. This has consequences for how we use language about emptiness and fullness. A region of space with no particles, in the everyday sense, is not a region of nothingness. It is a region where fields are close to their lowest energy states, still capable of supporting fluctuations and of transmitting influences. Light can pass through. Gravitational waves can distort distances. Virtual excitations can briefly appear and alter how real particles behave. The vacuum is not an empty container waiting to be filled. It is a particular state of the fields themselves. Quantum field theory does not settle the old philosophical questions about what is fundamentally real. It does, however, force us to reconsider how we connect those questions to the images in our heads. If every particle is a ripple, and every ripple is a state of a field, then the idea of matter being made of basic stuff becomes less compelling. The world looks more like a hierarchy of patterns in underlying structures than a pile of bricks resting on a final layer. This is not an invitation to despair or to declare that nothing exists. The chair is still there. The body is still there. They are as real as anything we know, but their reality is not that of solid kernels. It is the reality of stable processes, of standing waves, of patterns that sustain themselves as energy and information move through fields. In this view, to ask what something is made of is to ask which fields are excited, in what ways, and how those excitations hold together. There is no promise that the list of fields we know now is final. There may be deeper structures still, but the direction of travel is clear. The more we refine our theories, the more substance turns into structure, and the more the question made of what bends toward a different kind of curiosity. How does this pattern persist, and what does that persistence depend on? Patterns do not just sit there. They lean on each other, nudge each other, hold and break each other. And we give those ways of leaning a simple name: forces. In everyday language, a force is a push or a pull. You push a door, gravity pulls you toward the floor, friction slows you down. It sounds simple, but beneath that simplicity, modern physics finds only fields changing other fields, patterns shaping other patterns. What we call a force is really a habit of interaction. At the scales we know how to describe, there are four fundamental ways that fields interact. Four voices in the conversation, even when no one is speaking. One ties mass to mass and curves the paths of planets. One ties charge to charge and shapes chemistry and light. One binds quarks into protons and neutrons. One allows particles to change identity, turning one kind of matter into another. We label them with compact names: gravity, electromagnetism, the strong interaction, the weak interaction. The labels are familiar, but the story they tell inside quantum field theory is less so. It does not start with objects pulling each other. It starts with the requirement that certain symmetries be respected. A symmetry, in this context, is not about mirror images. It is a rule that says, if you perform a certain operation on the system, the underlying laws do not change. Rotate an experiment by some angle, and the basic equations stay the same. Shift everything in space by some distance, and the rules that relate causes and effects are unchanged. Slide forward in time, and the same relations still hold. These are symmetries we experience without naming them. In quantum field theory, there are more subtle symmetries, internal ones that do not correspond to literal movements in space, but to rotations in abstract spaces of phases and charges. When you require that the equations remain the same under these internal transformations, you are forced to introduce certain kinds of fields that mediate interactions. Those mediator fields give rise to particles that carry the forces. The technical term for such a carrier is a gauge boson. Gauge refers to the symmetry being enforced. Boson refers to a kind of particle that likes to pile into the same state as others of its kind. Unlike fermions, which obey exclusion rules. This sounds very far from pushing a door, yet it is all of a piece. The electromagnetic interaction, for instance, is the way that charged fields respond to a symmetry related to their phase, a kind of internal angle associated with the complex numbers in their description. Demanding that the theory be indifferent to shifts in that phase, and that this indifference hold at every point in space and time, forces the introduction of a field that compensates for those shifts. That compensating field is the electromagnetic field. Its quanta, when we look at them as particles, are photons. So when two electrons repel each other, the simple story is that two negatively charged particles push apart. The field story is that the electron field and the electromagnetic field are coupled. A disturbance in one influences the other, and that influence shows up in our detectors and our bodies as a push. The electron and the photon are not little pellets throwing invisible punches, but nodes in a web of symmetry and response. The strong interaction, which holds quarks together inside protons and neutrons, fits the same pattern in a more intricate way. Quarks carry a kind of charge called color, which has nothing to do with visible color and everything to do with how the strong force works. There are three types of color charge, often labeled in analogy with red, green, and blue, and their opposites called anti-colors. A symmetry that permutes these colors, demanding that the equations treat all such rotations equivalently, requires the existence of a field that keeps track of these transformations. Its quanta are gluons. Gluons not only carry the strong interaction, they themselves carry color charge. That means they interact with one another, making the strong force very different from electromagnetism. Between quarks, the strong force does not weaken steadily with distance the way the electric force does. When you try to pull quarks apart, the energy in the field between them grows, like stretching an increasingly stubborn string. At some point, it becomes favorable to create a new quark and antiquark from that energy, and the field relieves its tension by making more particles rather than letting the originals separate. This is confinement. Quarks are trapped inside hadrons, never seen in isolation. At very short distances and very high energies, something perhaps even more counterintuitive happens. The strong interaction becomes weaker. Quarks inside a proton, when probed at very small scales, behave almost like free particles. This behavior is called asymptotic freedom. Asymptotic here means in the limit, and freedom means that the interaction strength tends towards zero as the distance tends towards zero. So the strong force is strong at larger separations, confining quarks, and weaker at tiny separations, letting them act almost independently. A force that is both confining and freeing, depending on how closely you look, already hints that our everyday intuition about pulls and pushes is not a reliable guide. The weak interaction, by contrast, is the most elusive in everyday life. It does not hold structures together. It changes things from one state to another. It allows one type of particle to turn into another by emitting or absorbing certain quanta. These processes underlie radioactive decay, in which a neutron inside a nucleus can transform into a proton, an electron, and an antineutrino, or other similar transformations. Without the weak interaction, the sun would not shine in the way it does, because many of the reactions that turn hydrogen into helium involve weak processes. The carriers of the weak interaction are particles called W and Z bosons. Unlike photons and gluons, which are massless in the simplest sense, the W and Z bosons have large masses. Mass here means that they require a lot of energy to produce and that they do not travel far before decaying. That heaviness makes the weak force very short-ranged. Its influence becomes significant only at very small distances and very high energies. There is a story behind that mass. In the mathematical structure of the theory, the electromagnetic and weak interactions are two aspects of a single electro-weak interaction. At very high energies, the differences between them fade. The symmetry that unites them is clear. As the universe cools or as we work at lower energies, that symmetry is hidden, broken by the presence of another field that fills all of space. The Higgs field. The Higgs field is introduced to allow particles to acquire mass without spoiling the symmetries needed for the theory to make sense. In everyday words, it is a field whose non-zero background value throughout space changes how other fields behave. Particles that couple strongly to the Higgs field behave as if they are heavy. Those that couple weakly behave as if they are light or massless. The quanta of excitations in the Higgs field are Higgs bosons, detected in high-energy collisions as transient particles that decay quickly into lighter ones. It can be helpful to think of this loosely as movement through a medium. Not a medium you could pour into a jar, but a medium in the sense of a background property that is everywhere. Fields that interact with the Higgs field feel resistance when they try to change their state of motion. We read that resistance as inertial mass, the tendency of an object to resist acceleration. In this way, mass is not a hidden chunk of stuff trapped inside a particle. It is a symptom of how that particle's field responds to the Higgs field that pervades the vacuum. The fourth interaction, gravity, sits in an odd position relative to the others. In the language of general relativity, gravity is not seen as a force at all, but as the curvature of space-time caused by mass and energy. Objects follow the straightest available paths in a curved geometry, and we feel those paths as falls and orbits. This geometric view coexists uneasily with the quantum field view of other forces. There are tentative ways to describe gravity in terms of a field whose quanta would be gravitons, but a complete, consistent quantum field theory of gravity that works in all regimes has not been achieved. Even so, we can say this much: gravity governs the large-scale structure of the universe. It shapes galaxies, bends light, and sculpts the expansion of space. Electromagnetism and the strong and weak interactions govern almost everything that happens at atomic and subatomic scales. Together, these four interactions account for nearly all known physical processes. Yet their differences in range, strength, and character reveal how varied the ways of interaction can be. When we speak of strength here, it helps to be clear. Physicists often talk about coupling constants, numbers that measure how strongly fields interact. The strong interaction has, at the scale of typical nuclear processes, a large coupling. The electromagnetic interaction has a smaller one. The weak interaction is smaller still. Gravity, between individual particles, is by far the weakest. That is why you can pick up a paperclip with a small magnet and overcome the gravitational pull of an entire planet. The magnet is exploiting the electromagnetic interaction, which is much stronger than gravity at short distances. These comparisons rely on careful measurements and precise theory, but what matters for our purpose is the shape of the story. The universe is not tied together by one kind of glue. It is a conversation among fields, spoken in four main dialects. In this light, the old sentence, "Object A exerts a force on object B," is a compressed summary of a much richer description. There is no object in isolation. There are fields, and where their excitations overlap or influence each other, we perceive pushes, pulls, and transformations. The wooden table, the iron core of the Earth, a streak of radioactive material, a star burning hydrogen, all are particular ways these interactions show up at larger scales. At human scales, we do not see gauge bosons or Higgs fields. We see weight, friction, warmth, pressure. But underneath, weight is gravitational interaction in curved space-time. Friction is electromagnetic interaction between electron clouds in rough surfaces, converting organized motion into disordered vibration. Warmth is random motion of particles and the exchange of photons. Pressure is particles colliding. Electromagnetic repulsions maintaining distance. The comfortable nouns are summaries of countless field interactions we do not notice. there is a subtle philosophical turn hiding here. Once we describe forces as ways in which fields talk to each other, the picture of matter as a pile of self-sufficient things grows even thinner. A proton is not just three quarks. It is three quark fields in a bound pattern, tied together by gluon fields. An atom is not just a nucleus and electrons. It is a balance of electron and nuclear fields held in place by the electromagnetic interaction. A solid is not just atoms packed together. It is a regular arrangement of atomic fields whose collective excitations behave like new particles, such as phonons, quanta of vibrational modes. At each level, the stability of what we call a thing depends on the ongoing interplay of forces. Turn off one of the interactions, even as a thought experiment, and familiar structures dissolve. Without the strong interaction, nuclei cannot exist. Without electromagnetism, atoms cannot form. Without the weak interaction, many nuclear processes stall. Without gravity, stars and galaxies do not gather. The existence of the patterns we move through owes itself to the continuity of these interactions, not to a basic substance that would remain the same in their absence. When we return to the simple question, what is it made of? The answer now carries more context. A person sitting on a chair is made of quark and lepton fields. Of electron and quark excitations, yes. But they are also made of how those excitations are joined and held by the four interactions. Identity is distributed over relations. The chair and the person remain distinct only because the interactions organize fields into relatively stable arrangements. Those arrangements are real, but they do not float above the web that sustains them. This way of seeing offers no final comfort, but it does offer a certain kind of clarity. We look for a foundational stuff, and instead find structured emptiness, filled with fields that never completely rest, conversing in four main tones. Matter, under that light, is not a list of ingredients but a score of interactions, played and replayed until patterns emerge that are stable enough for us to call them things. At some point, someone tried to write that score down on a single page, as if the universe could be summarized in a finite set of notes. What emerged from that effort is what physicists now call the Standard Model. The name sounds modest, almost bureaucratic, like the label on a form. It is anything but. Behind it sits a compact set of equations that describe, with extraordinary success, almost everything we see in laboratories. How particles scatter, how atoms hold together, how light and matter interact, how unstable particles decay. If we strip away the technical clothing, the picture is this. There is a collection of matter fields, a collection of force fields, and one special field that gives many of the others their mass. The matter fields come in two broad families. One family is made of particles called quarks, which feel all the forces except, in practice, the weakest one at human scales. The other family is made of particles called leptons, which include the electron and its cousins, and tiny neutral particles called neutrinos. Quarks come in 6 varieties, or flavors, with names that sound more like nicknames than ingredients: up, down, charm, strange, bottom, and top. Up and down are the lightest and most familiar. They combine to form protons and neutrons, which in turn build up atomic nuclei. The heavier flavors appear in high-energy processes and decay quickly into lighter particles. Leptons also come in 6 types: the electron, 2 heavier versions called the muon and the tau, and a neutrino associated with each of them. Neutrinos are extremely light and interact only weakly, passing through enormous amounts of matter almost without noticing. The force fields are associated with the interactions we have already walked through. There is the electromagnetic field, whose quanta are photons. There is the strong field, whose quanta are gluons, binding quarks into hadrons. There are fields associated with the weak interaction, whose quanta are the W and Z bosons. Each of these carries specific charges and spins, properties that determine how they behave and how they can transform. Sitting alongside them is the Higgs field, a scalar field in the language of the theory, meaning that at each point in space and time, it is described by a single number rather than a direction or more complex structure. Unlike many other fields, the Higgs field does not relax to zero in its lowest energy state. Its lowest energy configuration has a non-zero value everywhere, like a background hum that never turns off. That ever-present value is what allows many other particles to behave as if they have mass. In the Standard Model, then, every particle you have heard named is either a stable or unstable excitation of one of these fields. A proton is mainly a bound state of up and down quark fields, stitched together by gluon fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. A Higgs boson, when briefly created in a very energetic collision, is an excitation of the Higgs field, a ripple on top of the background value. It is tempting to imagine this as a kind of periodic table of the deep world. A small number of fundamental fields, a small number of interaction rules, and from them, everything else. There is some truth in that image. At energies accessible to our largest accelerators, and in experiments done so far, this framework accounts for a vast range of phenomena. The probability that a given process will occur, the spectrum of particles produced in a collision, the lifetimes of unstable particles, the scattering angles seen in detectors, all match the Standard Model's predictions with impressive precision. One of the most dramatic tests of this structure took place in a ring of tunnels buried under the countryside near a European border. In that ring, protons are accelerated to energies far beyond anything in ordinary experience, and then smashed together. The ring is many kilometers around. Beams of particles travel around it again and again, guided by powerful magnets, before colliding in detectors the size of buildings. The goal of such collisions is not destruction for its own sake. It is to concentrate enough energy in a small enough region that rare processes can occur. Processes that would have been common in the very early universe but are now almost impossible in natural conditions. Among those hoped-for events was the appearance of the Higgs boson, the quantum of the Higgs field. According to the theory, particles gain mass through their interaction with the Higgs field's background value. But the direct signature of that field's excitation is a particle that should be heavy and extremely short-lived. When the data were analyzed, careful and slowly, a pattern emerged. An excess of events in which certain combinations of lighter particles appeared, with energies consistent with the decay products of a particle of a particular mass. The conclusion, reached with statistical care, was that a new particle had been observed, matching the characteristics of the Higgs boson predicted by the Standard Model. From one angle, this was the last major missing piece of a puzzle. The menu of fields was now complete. The matter fields, with their quarks and leptons, the force fields with their photons, gluons, and weak bosons, and the Higgs field that ties many of their masses together, all had experimental support. The Standard Model could claim to be an almost complete description of the microphysics of ordinary matter and its interaction. From another angle, the success was unsettling. The more precisely experiments confirmed the theory, the more the theory's limitations came into focus. The Standard Model does not include gravity in its quantum field form. It does not explain why the values of its many parameters are what they are. It does not, on its own, account for the existence of dark matter, an unseen form of matter whose gravitational effects are visible in the motion of stars and galaxies. It does not explain dark energy, a name given to the cause of the observed accelerated expansion of the universe. Cosmological measurements suggest that the kind of matter the Standard Model describes directly, often called ordinary or baryonic matter, makes up only a small fraction of the total energy content of the universe. The rest is divided between dark matter and dark energy, whose nature remains uncertain. That means that the tidy set of fields and interactions we have written down accounts, in its current form, for only a minority of what is out there. Even within its domain, the Standard Model raises as many philosophical questions as it answers. It tells us that what we call a particle is an excitation of a field. It lists those fields and the allowed excitations. It provides rules for how they interact. But it does not tell us why there are exactly 3 generations of quarks and leptons, each heavier than the last, with the same pattern of charges. It does not say why the strengths of the interactions take the values they do. or why the Higgs field's background value is what it is. At a more concrete level, the Standard Model implies that if you were to take all the ordinary matter in the observable universe and count the particles, the number would be vast, on the order of 10 to the power of 80. And yet, on average, there would be only around one mass-carrying particle per cubic meter of space. Between stars, the vacuum is nearly perfect by everyday standards. The feeling that the world is densely filled with stuff is a scale-dependent illusion born of the fact that we live near the surfaces of planets, in the thin skins where matter has clumped. This tension between apparent fullness and actual sparseness mirrors the deeper tension between substance and structure. The Standard Model does not say that matter is made of tiny solid pellets. It says that matter is patterns of excitation of a small set of fields, usually in their lowest or near lowest energy configurations, rarely excited individually at the scales we inhabit. To call a table solid is to make a statement about how these patterns resist deformation when pushed, not about microscopic grains of material pressed against each other without gaps. Some of the terms used here can sound forbidding but carry simple roles. A lepton is a matter particle that does not feel the strong interaction. The electron is one. A quark is a matter particle that does feel the strong interaction and carries color charge. A boson is a particle associated with a field whose quanta compile into the same state, often force carriers or collective excitations. The photon is such a boson. A scalar field is one that assigns a single numerical value to each point in spacetime, rather than a direction or more complex object. The Higgs field is of this type. The more we translate the equations into words, the clearer the overall flavor becomes. This is a theory of relationships and symmetries, not a catalogue of ultimate substances. You will not find, in the Standard Model, a statement that the universe is made of a particular kind of stuff in the old sense. Instead, you find that the universe is described by a particular set of fields, and that the excitations of those fields, governed by symmetries and conservation laws, behave in ways that match what we see. There is a quiet existential ripple in this. For a long time, the search for what things are made of carried the hope of a final answer, a layer where explanation would stop. The Standard Model comes as close as any framework yet has to that role in particle physics. It is astonishingly accurate. It gives us a coherent language for nearly all known non-gravitational phenomena at accessible energies. And yet, instead of a solid floor, it offers an elegant web and then gestures beyond itself to what it does not include. If matter is nothing but field excitations, and if the fields we have mapped account for only a sliver of the total energy content of the cosmos, then the old comfort that comes from believing we have found what everything is made of becomes hard to sustain. We are left instead with a more fragile understanding. The part of the world we can probe in detail is structured by a small, well-tested set of rules. Those rules operate on entities that are not things but patterns. Beyond that, there is more, and the theory itself admits it. The phrase, almost everything, in this context, hides a careful humility. The Standard Model is not being sold as a theory of all reality. It is a theory of a certain range of experiments, a certain range of energies and scales, and within that range, it works brilliantly. Outside that range, in regions of extreme gravity, at energies far above those we can reach, or in the behavior of dark matter and dark energy, it is silent or incomplete. From the point of view of our guiding question, this is enough to change the ground under our feet. The best framework we have for describing matter at small scales does not support the idea that things are made of tiny bits of substance. It supports the idea that things are stable ways in which fields can be arranged. The word "made" itself begins to feel like a metaphor we forgot was a metaphor. What the Standard Model gives us, then, is not a final list of ingredients, but a proof of concept. A demonstration that the world can be described, to a remarkable extent, without ever appealing to a fundamental stuff, only to fields, their symmetries, and their interactions. What remains is to see what happens to our picture of reality and of ourselves when we take that seriously and follow it to the places where the theory starts to fray. At the edge of that web, something heavy waits, insisting that the picture is still incomplete. The fields of the Standard Model live on a stage that, in the equations, is taken for granted. Space and time are there from the beginning. A fixed backdrop with a simple geometry. You can specify a point by 3 numbers for space and 1 for time, and the distances between points are given by a rule that never changes. The fields ripple and interact on this stage, but the stage itself does not respond. It is like a perfectly rigid canvas that never bends no matter how much paint you pile on it. Gravity refuses that role. It does not sit alongside the other forces as just another way fields talk to each other. It reaches deeper, into the structure of space and time themselves. When we follow it carefully, the background turns into part of the cast. The first hints came from simple puzzles about motion and light. In the old picture, space and time were separate. Time ticked the same everywhere. Space was a 3-dimensional grid where you could place objects and measure their positions. Motion was defined relative to this fixed frame. Gravity, in that setting, was a force that pulled masses toward one another, decreasing with distance but always acting instantly, as if each mass knew what the others were doing in the same moment. But light refused to fit neatly into that scheme. Experiments showed that its speed, in a vacuum, is the same for all observers who move at constant speeds relative to each other. No matter how fast they are going, that constancy clashes with the idea of a universal time and a simple addition of velocities. To reconcile the facts, the structure of space and time had to be rewritten. The result was special relativity, which treats space and time as aspects of a single 4-dimensional entity, space-time. In this framework, what one observer calls space and another calls time can mix, depending on their relative motion. Events that are simultaneous in one frame are not necessarily simultaneous in another. Distances and durations become relative, but the space-time interval between events, a particular combination of space and time differences, remains the same for all. Space-time, in this sense, is not a thing we can picture easily. It is a mathematical structure that tells us how to compute intervals and how objects move if no forces act on them. In special relativity, the geometry of space-time is flat. Straight lines stay straight. Parallel lines remain parallel. And the rules for measuring intervals are the same everywhere. Gravity, however, kept misbehaving when treated as just another force in that flat space-time. There was a stubborn coincidence. The mass that measures how strongly something feels gravity is the same as the mass that measures how much it resists acceleration from any force. Drop a hammer and a feather in a vacuum, and they fall the same way, despite having different masses and compositions. This equality, called the equivalence of inertial and gravitational mass, suggested a deeper connection. The step that followed was both simple and radical. Instead of thinking of gravity as a force pulling objects, imagine that what we experience as falling is simply following the straightest possible path in a space-time whose geometry has been curved by the presence of mass and energy. A straight path in a curved space can look like a curve to someone who expects space to be flat. The apple does not feel a mysterious pull. It is moving freely along a path that the curved space-time dictates. This is the central idea of general relativity. Space-time is no longer a rigid background. It is dynamic, responsive. The distribution of mass and energy tells space-time how to curve. The curvature of space-time tells matter and light how to move. Mathematically, this is expressed in terms of a metric, a rule that defines distances, and curvature, a measure of how that rule changes from place to place. Physically, it means that gravity is geometry. One way to bring this closer to intuition without pretending it is simple is to think about straight lines on different surfaces. On a flat sheet, the shortest path between 2 points is a straight segment that you can draw with a ruler. On a sphere, like the Earth, the analog of a straight line is a great circle, such as the equator or the path of an airplane flying along a route of minimal distance. 2 such paths can start out parallel at the equator and then converge at a pole. That convergence is a sign of curvature. In general relativity, Something similar happens in space-time, and the focusing of paths shows up as gravitational attraction. In this picture, light also responds to curvature. Light always follows paths that, locally, are as straight as possible for something that moves at the speed of light. When space-time is curved, those paths bend. That is why light from a distant star can be deflected when it passes near a massive object, a phenomenon called gravitational lensing. It is why light climbing out of a gravitational well loses energy and shifts to longer wavelengths, a redshift caused not by motion but by the geometry itself. General relativity does more than reinterpret falling. It predicts new phenomena. One is the existence of black holes, regions where space-time is curved so intensely that within a certain boundary, called the event horizon, all paths forward in time lead deeper inward. Nothing, not even light, can escape once it is inside that horizon. At the center of an idealized black hole, the equations suggest a singularity, a place where curvature becomes infinite and the theory itself breaks down. Another prediction is the existence of gravitational waves, ripples in the curvature of space-time that propagate outward when massive objects accelerate asymmetrically, such as two heavy stars spiraling around each other. These waves carry energy away, stretching and squeezing distances as they pass. After a century of being purely theoretical, they were detected by instruments that measure tiny changes in the lengths of long arms using laser light. The changes are minuscule compared to any human scale, but they matched the patterns expected from distant collisions of black holes and neutron stars. All of this paints a coherent, elegant picture of gravity as geometry, but it floats uncomfortably alongside the quantum field description of the other interactions. In the Standard Model, fields live in space-time, but do not alter its basic structure. In general relativity, space-time itself is a dynamic participant. We have, in effect, two separate theories. One that excels at describing the small and fast in regimes where gravity is weak, and one that excels at describing the large and heavy where quantum effects can be ignored. The trouble becomes acute when we look at situations where both quantum and gravitational effects should matter. Near the center of a black hole, in the earliest fractions of a second after the Big Bang, when the universe was unimaginably hot and dense. In such regimes, space-time curvature is extreme, and quantum fluctuations should be violent. There, we do not have a single agreed-upon framework. One way to try to bridge the gap is to apply the techniques of quantum field theory to the gravitational field itself, treating small ripples in space-time as a field with its own quanta, gravitons. Gravitons, if they exist, would be massless particles with spin 2, mediating the gravitational interaction in a way analogous to photons in electromagnetism. At low energies and weak fields, this approach reproduces the predictions of general relativity remarkably well. However, when one pushes these calculations to higher energies, infinities appear that cannot be tamed by the usual methods of renormalization, the procedures that work for other quantum fields. The theory becomes non-renormalizable in the technical sense, meaning that an infinite number of parameters would be needed to absorb the divergences. That robs it of predictive power. At some scale, which we estimate using combinations of fundamental constants and call the Planck scale, the existing methods stop making sense. The Planck scale is set by combining the gravitational constant, the speed of light, and Planck's constant, a quantum of action, into quantities with units of length, time, and energy. The Planck length is the distance at which quantum fluctuations of spacetime itself are expected to become significant. The numbers involved are so small and so large that saying them aloud changes nothing for intuition. What matters is the idea. There is a regime where we expect both quantum effects and gravity to be strong, and our current theories, separately brilliant, do not agree on a common language there. Other approaches, such as string theory and loop quantum gravity, attempt to construct a more fundamental framework in which space-time and matter emerge from deeper structures. In string theory, the basic objects are extended. one-dimensional entities whose vibrational modes appear as different particles, including, in some versions, the graviton. In loop quantum gravity, space-time itself is treated as having a discrete, network-like structure at the smallest scales, with space built from finite loops. These attempts are rich and mathematically sophisticated. They offer glimpses of how gravity and quantum mechanics might fit together, yet none has achieved the same level of experimental confirmation as the Standard Model or general relativity. They remain, for now, proposals, constrained by the difficulty of probing the relevant scales in any direct way. There is a deeper question under all this. In quantum field theory, we started with a space-time stage and put our fields on it. The properties of that stage were given in advance. In general relativity, the stage itself becomes a player, shaped by the actors on it. A complete theory would have to say something about what space-time is, not just how things move within it. Is space-time a field like any other, with its own quanta and excitations? Is it a kind of emergent structure that arises from more fundamental degrees of freedom we have not yet identified? Is the separation between space, time, and matter an artifact of how we currently write our equations? At a more personal level, gravity is the first interaction any of us encounters. It kept you on the ground as a child. It shapes the sense of up and down, the rhythm of walking, the falling of objects. It is so pervasive that it feels like the essence of solidity itself. To learn that gravity is not a pull from a hidden substance, but a reflection of curved space-time, and that even this picture fails at certain scales, is to discover that one of the most basic features of experience is born from a structure that is more enigmatic than solid. We began with a question about what matter is made of. Gravity answers from a slant. It suggests that, at least at cosmic scales, the right question might be what shapes the stage on which matter appears. And when we try to fold gravity into the same field language as the rest, gravity answers again. I am not just one more force among others. I change the meaning of distance and time themselves. In that refusal, there is both frustration and a strange kind of honesty. The world is telling us that our wish for a single, simple substance, or even a single, simple framework, may not be granted. Space, time, matter, energy, fields, curvature. These may all be aspects of something deeper, something that will not easily fit into the grammar of made of at all. So it is not surprising that, having watched the stage itself begin to move, we started wondering whether there was some hidden rulebook just out of sight, a place where even space-time and fields are only temporary players. When people talk about going beyond current physics, it can sound like a search for more exotic particles, or a bigger accelerator, or a new kind of telescope. But underneath those ambitions is a quieter desire to understand the rules that make space-time and fields possible at all. Not just what the pieces are, but why there are pieces and why they follow these particular patterns. One route into that question begins with a simple complaint. In quantum field theory, particles are treated as points. A point has no size. That makes the mathematics neat, but it also means that when particles interact at extremely short distances, certain calculated quantities try to become infinite. For the forces of the Standard Model, clever techniques can absorb those infinities into a small set of measurable parameters. For gravity, those techniques fail. So one idea is, perhaps particles are not points. Perhaps the basic objects are extended, however slightly. Not beads, but tiny strings. A string, however short, can vibrate in many ways. Each vibrational mode has a characteristic energy, and energy is tied to mass and other properties. In string theory, what we call a particle is one possible vibrational pattern of a fundamental string. One pattern behaves, at low energies, like a photon. Another behaves like an electron. Another, in certain versions, behaves like a graviton, a quantum of the gravitational field. The attraction of this picture is that it softens the violent interactions at very short distances. A string cannot probe arbitrarily tiny scales the way a point can. When you try to push two strings together beyond a certain limit, their extended nature smears out the interaction. The infinities that plagued point-like particles are tamed. Gravity appears not as an awkward extra, but as one more vibrational mode of the string. Of course, the theory brings its own demands. Strings do not behave consistently in a world with only 3 dimensions of space and 1 of time. The mathematics insists on more spatial dimensions than the ones we see. The exact count depends on the version, but it is always more than the familiar 3. To reconcile that with experience, those extra dimensions are imagined as curled up, compactified on scales so tiny that we never notice them directly. A way to picture this, loosely, is to think of an ordinary hosepipe lying on the ground. From far away, it looks like a line, one-dimensional. Come close, and you see that at each point along the line there is a circular direction. The roundness of the hose. If you are much smaller than the hose, you can move along that circular direction as well as along the length. In some versions of string theory, every point in our large 3-dimensional space has additional curled directions attached to it, like tiny internal spaces. Strings can vibrate and wrap around those internal directions, and the way they do so helps determine what kinds of particles appear. This is both a gift and a problem. It is a gift because it gives string theory enormous flexibility. Many different shapes for the extra dimensions lead to many different possible low-energy worlds, with different particles and force strengths. It is a problem because that flexibility makes it difficult to extract sharp predictions. Instead of one unique outcome, there may be a vast landscape of possible effective universes, all consistent with the basic string rules, only some of which resemble ours. Technical terms here hide simple roles. Compactification just means curling up extra dimensions so that they are small and hidden. A landscape is a metaphor for the enormous set of possible configurations of those curled dimensions and the fields living on them, each configuration corresponding to a different set of low-energy laws. From an experimental point of view, that means string theory is more like a space of candidate explanations than a single fully specified model of our world. Another route to quantum gravity starts from the opposite side. Instead of softening particles, it takes the geometric insight of general relativity as fundamental and tries to quantize geometry itself. If gravity is curvature of space-time, perhaps we should apply quantum ideas directly to that curvature, without starting from a fixed background. In loop quantum gravity, space-time is not assumed to be smooth all the way down. Instead, the mathematical structures that describe geometry are written in a form that naturally decomposes into finite, network-like pieces. Areas and volumes become quantized. They can take only certain discrete values, not any arbitrary value. At the smallest scales, space is represented by graphs called spin networks, where edges and nodes carry labels that encode quantum information about geometry. As these networks evolve, they form higher dimensional structures, sometimes called spin foams, which represent a kind of quantum history of spacetime. If this sounds abstract, that is because it is. There is no easy picture of a spin network in ordinary 3-dimensional space, because the network is, in a sense, space itself, not something placed inside it. The main idea, though, can be put simply. Space is not infinitely divisible. There is a lower limit to how finely you can chop it, and that limit is built into the theory as a fundamental graininess of geometry. This graininess shows up only at scales far, far smaller than any we can probe directly. At familiar scales, the discrete structure smooths out, much as the individual molecules in a fluid become irrelevant for describing a wave on the surface of the sea. But if loop quantum gravity, or something like it, is right, then the continuum picture of spacetime in general relativity is an approximation, just as the picture of matter as a continuous medium is an approximation on top of atoms. Both of these approaches, strings and loops, are attempts to answer the same challenge. What happens at the scale where quantum uncertainty and spacetime curvature are both essential? That scale is often called the Planck scale. after the physicist whose constant sets the granularity of quantum action. The Planck length, Planck time, and Planck energy define a regime where our current separate theories are expected to fail. They are not just numbers. They are signposts that mark the boundary of our tested understanding. To probe smaller distances, we generally need higher energies. This is the logic of particle accelerators. The more energy you can concentrate into a collision, the smaller the structures you can resolve. But that logic runs into an obstacle. If you concentrate enough energy into a region small enough, gravity becomes strong. Beyond a certain point, the energy density is so high that the region collapses into a tiny black hole. The very act of trying to examine a smaller and smaller region produces an object that hides that region behind an event horizon. This suggests that there may be a fundamental limit to how finely we can investigate the structure of space-time, no matter how ingenious our instruments. It is not a technological limit, like saying we cannot build a large enough machine. It is a conceptual limit, rooted in the interplay of quantum theory and gravity. To look more closely, we must add energy. Add too much, and what we want to see disappears from view behind a horizon of its own making. If something like that limit is real, the Planck scale is not just a funny set of units. It is a threshold beyond which the question, what is inside this, loses empirical meaning. We can build models, but we cannot directly watch them in action. We are left inferring, guessing, and testing only the indirect consequences at larger scales. That does not mean the search is pointless. Even without direct access, the consistency of our theories sets strong constraints, demanding that string theory reduce to general relativity and the standard model in the right limits restricts what shapes the extra dimensions can take. Demanding that loop, quantum gravity reproduce smooth spacetime at larger scales constrains how spin networks can behave. Observations of black holes, gravitational waves, and the cosmic microwave background may, over time, reveal subtle signatures of whatever the correct theory is. But there is a shift in mood here. Up to a point, physics has been driven by the belief that if we build a more powerful microscope, a bigger accelerator, a more sensitive detector, the world will reveal smaller and smaller pieces. The Planck scale and the difficulties around it hint that the world may not be organized for that kind of inspection all the way down. There may be a layer where asking for a smaller piece is like asking for a temperature of a single molecule. The words stop matching the reality. In that light, strings and loops are not just technical constructs. They are expressions of a deeper unease with our current picture and of a refusal to give up on coherence. They say, there must be some way to describe space-time and matter within one framework, some set of rules that makes both quantum uncertainty and curvature natural. Whether either of these proposals, or something yet unimagined, will turn out to be right is an open question. For our purposes, what matters is what they imply about the question we began with. If space-time itself is woven from more basic structures, or if particles are different notes of extended strings vibrating in hidden dimensions, then asking what matter is made of becomes less and less about stuff and more about pattern. The supposed referee we hope to catch in the act may not be a thing at all, but a set of relationships we can only ever approach indirectly through the behavior of the world at scales we can reach. There is a kind of humility in that recognition, and also a kind of freedom. If there is a fundamental limit to how deeply we can dissect reality, then the dream of total transparency of pulling back every curtain is replaced by something softer. We are not owners of the universe's blueprint. We are participants in patterns we only partially understand, tracing their outlines from within. From inside those patterns, the question that began this whole journey comes back changed, like a voice you recognize but cannot place anymore. We started with a simple habit of thought. When you hold an object in your hand, it feels natural to imagine it as built from smaller objects. A table made of wood, wood made of fibers, fibers made of molecules, molecules made of atoms, atoms made of protons, neutrons, and electrons. Each layer explained by a deeper layer of stuff. Follow that chain with what we now know, and the story loosens. Protons and neutrons are not little stones. They are bound states of quarks and gluons, which are excitations of fields. Electrons are excitations of another field. Photons are excitations of the electromagnetic field. The Higgs boson is an excitation of the Higgs field. In the language of our best theories, the world is not composed of tiny pellets. It is organized patterns of fields, interacting. That does not mean nothing is real. It means that the word substance, in the old sense of a solid underlying stuff, no longer fits well. When you ask what an electron is made of, there is no answer of the form smaller pieces of matter inside it. There is only, it is the electron field, excited in a particular, minimal way. That is not a smaller brick. It is a different category entirely. To call matter not made of anything is shorthand for this shift. It does not deny that the world exists. It denies that the world is built, at bottom, from chunks of a more fundamental material. The search for the last grain has been replaced by a description in which the basic entities are fields and their relationships, and in which what we call things are stable patterns in that web. Pattern here is not an airy metaphor. A pattern is a configuration that persists and can be recognized across time. A whirlpool in a river is a pattern. Water flows through. The molecules do not stay, but the shape and behavior endure. A flame is a pattern. Fuel enters, hot gases leave, but the flame keeps its approximate form. In a similar way, a proton is a pattern of quark and gluon fields. A crystal is a pattern of atomic positions and bonds. A living cell is a pattern of molecules and reactions. The crucial point is that the identity of the pattern does not depend on the permanence of its constituents, but on the stability of the arrangement. The water in a whirlpool changes. The atoms in your body are exchanged over years through food, air, and waste. Yet the whirlpool remains recognizable. You remain, in some sense, yourself. What endures is organization, not substance. Physics, pushed hard enough, seems to tell us that matter itself is that kind of thing, not a lump of stuff, but a hierarchy of organized excitations of fields. The chair, the stone, the tree, the body are layers of patterns. Atomic, molecular, cellular, structural. The fields are more basic than any of these layers, but even a field is not a chunk of matter. A field is a set of values extending through space-time, a rule assigning strengths and phases and potentials to each point. It is defined more by what it does and how it transforms than by what it is made of. This brings us close to a different way of speaking. Instead of asking what is the world made of, we might ask what kinds of patterns and processes can exist, under which rules, and how they persist or dissolve. The laws of physics, in this view, are constraints on possible patterns. They do not specify a material. They specify what structures and behaviors are allowed in the space of possibilities. The phrase laws of physics can sound grand, but it just means regularities we have distilled from experience and expressed mathematically. They are not commandments written outside the universe. They are compact summaries of observed symmetries and conservation rules. Energy is conserved. Momentum is conserved. Certain charges are conserved. The equations that encode these facts tell us which field configurations can arise and how they evolve. Matter, then, is not a separate ingredient poured into those equations. It is what certain solutions look like. A solution here means a particular way the fields can be arranged that satisfies the equations over time. Some solutions correspond to particles flying apart. Some correspond to atoms in a crystal. Some correspond to stars, galaxies, and perhaps entire universes. We inhabit a particular branch of that space of solutions. There is another layer to this, which sits at the boundary between physics and how we know anything at all. We do not have direct access to fields in themselves. What we have are measurement outcomes, detector clicks, tracks on photographic plates, flashes on screens, numbers recorded in experiments. The formalism of quantum theory gives us a way to assign probabilities to those outcomes based on a description of the state of the fields and the interactions involved. When we say there is an electron here, we are compressing a story. The longer version is, if we set up this apparatus and perform this measurement, we will, with high probability, see a certain pattern of results, and the best model we have for organizing those results uses a concept we call an electron, which is an excitation of a particular field with specific properties. The electron is not a small marble hiding behind appearances. It is the role played in our model by a certain stable set of regularities in what we observe. This does not reduce reality to mere observation. It does highlight that any claim about what is really there is mediated by a theory, a mapping from experimental setups and outcomes to concepts like field, particle, and interaction. When we take the phrase "not made of anything" seriously, we are also acknowledging this mediation. We are letting go of the idea that there is a mind-independent catalog of stuff whose nature we could know without reference to the ways we interact with it. In more formal language, some philosophers of physics talk about structures and relations as primary. The idea, put loosely, is that what is fundamental is not objects with intrinsic essences, but patterns of relations that satisfy certain symmetries and equations. A particle is a node in such a structure. A field is a way of encoding how those nodes are connected across space-time. We never see the nodes directly. We see the patterns they allow. Through experiments and experiences. You do not need the philosophical vocabulary to feel the consequence. If matter is patterns in fields, and if fields are defined by their behaviors and symmetries rather than by hidden substance, then the solidity you feel is a kind of emergent fact. Emergent here means arising at a composite level, not written explicitly at the most basic level. Solidity emerges when countless interactions between atoms produce a stiffness that resists deformation. Temperature emerges from the average motion of many molecules. Identity emerges from continuity and patterns over time. When we say matter is not made of anything, we are pointing to this hierarchy of emergence. Each level is made of the level below in a practical sense. A table is made of wood. Wood is made of cells. Cells are made of molecules. But if you keep going, there is no final level of stuff that is not itself describable as a configuration of something more abstract. The field description undercuts the image of a last solid layer. You might reasonably ask, if there is no last layer of stuff, what holds all this in place? The honest answer is that what holds it in place, as far as physics can say, are the stability properties of the patterns allowed by the laws. Certain configurations are dynamically stable. Disturb them a little and they return to a similar state. Others are unstable. Disturb them and they decay into something else. Atoms are stable in that way. So are many nuclei, chemical bonds, and large-scale structures under gravity. Your own body is a mixture of stable and unstable patterns. The atoms in a bone are, for practical purposes, stable over long periods. The molecules in a cell membrane are exchanged on shorter timescales. The patterns of neural activity underlying a memory may persist for years, but their physical substrate is in constant flux. The self you feel is not a lump of substance, but an ongoing process, a narrative written in matter that is itself a narrative of fields. Seen this way, the phrase "made of" gives way to something like unfolding as. The universe is not made of fields the way a house is made of bricks. It unfolds as interacting fields. Those fields, in turn, unfold as particles when measured, as forces when they influence other fields, as space-time curvature when mass and energy rearrange geometry. A chair unfolds as a particular, stable arrangement of these unfoldings, recognized by a brain that is itself another arrangement. There is a quiet vertigo in accepting this. The comfort of picturing reality as built from little solid beads gives way to a sense that what is real are processes, not pieces. But there is also a kind of coherence in it. The question, what is matter made of, led us down into models that, taken seriously, refuse the very premise of the question. Matter is not made of anything in the old sense. It is how fields behave when they settle into patterns that last long enough to feel like things. What we do with that insight, as individuals moving through a world of chairs and bodies and memories, is another question. For now, it is enough to notice that the ground under our intuitive picture has shifted. The floor is not a slab of substance. It is a pattern that keeps renewing itself, moment by moment, according to rules we have glimpsed, but do not fully command. The thought that there is no solid floor can feel like a loss. Until you realize you have been standing, this whole time, on something else. You are sitting on a chair, or lying on a bed, or leaning against a wall. Whatever the posture, there is some surface that says, quietly, enough, no further. At the microscopic level, that stopping is just fields refusing to overlap in certain ways. Electrons in your body and electrons in the chair arranging themselves so that pushing closer would cost too much energy. No pieces colliding, no tiny pillars holding you up. Only patterns that cannot occupy the same pattern space without changing into something else. From the inside, though, it does not feel like that. It feels like support. It feels like the world pushing back against your weight and saying, you are here. The solidity is not an illusion in the sense of being fake. It is an illusion in the sense that your nervous system reports the end result of billions of interactions and compresses them into a single wordless message. The same thing happens with your body. You can point to a hand, a chest, a face in a mirror. You can say, this is me. Underneath, that me is a shifting colony of cells. Those cells are collections of molecules. Those molecules are atoms. Those atoms are, as far as physics can tell, stable patterns in fields. At every level, material flows through. Food in, air in, waste out. The pattern persists. The contents do not. You have never been made of the same atoms for very long. Yet the sense of self, of continuity, is strong. That sense is not a property of any single particle. It is a property of arrangements that preserve enough structure over time to feel like a story. A story is not nothing. It has a beginning, a middle, and an end. It has characters, conflicts, threads that return. It can be told in different words and still be recognizably the same story. Your life is like that. The universe does not attach labels to field configurations saying, this is you. But there is, in the ongoing flux, a region of space-time where processes are densely coupled. Signals run along nerves. Memories form in changing networks of connections. The pattern is tight enough to refer back to itself and say, I. When physics tells you that matter is not made of anything in the old sense, it is also telling you that you are not, either. There is no little pearl of essence hidden behind your experiences, no final particle that is truly you and would remain if everything else peeled away. There is a pattern of relations, a way information is stored, processed, and updated in a living brain and body. That is not an insult. It is a recognition that what you are is more like a verb than a noun. This can be unsettling. If there is no fixed core, then what anchors you? If the chair, the room, the planet, the atoms of your body are all temporary gatherings of fields, what keeps anything from dissolving into indifference? Part of the answer is simple. The laws, or whatever deeper regularities they point to. Given the rules, some patterns are extremely likely to last at human timescales. Rock formations, planetary orbits, certain molecular structures. The conditions on Earth happen to be such that complex chemistry can occur, and over long stretches of time that chemistry has built increasingly intricate forms. You are one of them. The other part of the answer is less about physics and more about how you live with it. If there is no substance that guarantees your identity, then every act, every word, every choice becomes part of what holds that identity together. You are not revealing a pre-written self. You are continually writing it. Within constraints you did not choose, but now inhabit. The absence of a solid floor does not mean anything goes. It means that the floor is replaced by a web of constraints and possibilities. You cannot will yourself out of gravity or decide that electrons will stop repelling. But within the space those constraints carve out, there is room for different patterns of action, for kindness or cruelty, for attention or distraction, for honesty or self-deception. The physics does not dictate those choices. It only sets the stage on which they unfold. There is a strange symmetry here. When you sit on a chair, you trust that the chair will hold. You do not calculate forces. You let the pattern of matter under you carry your weight. The chair, in its own way, trusts the rules too. It is nothing but atoms arranged so that, under the usual stresses, they return to their shape instead of breaking. You and the chair are both leaning on the same invisible regularities, the same quiet stubbornness of fields. Now imagine turning the picture around. Instead of only the person sitting on the chair, imagine the universe sitting in the person. Not as a mystical metaphor, but as a simple physical fact. In your brain, there is a small, dynamic model of the world. It includes rough maps of rooms and streets. It includes the remembered faces of people. It includes symbols for atoms, stars, galaxies. It even includes, now, some version of quantum fields and curved space-time. None of those things exist as literal small objects in your head. They exist as patterns of neural activity, as changes in the strengths of connections between neurons. A neuron is a cell specialized to carry electrical and chemical signals. When it fires, it influences others. Over time, repeated activity carves pathways. Those pathways can stand in for aspects of the world, allowing you to predict, imagine, and plan. When you think about the universe as you understand it comes to life as a pattern, running on a pattern that sits on a planet that is a pattern born from earlier patterns. There is a loop. The world gives rise to creatures who can model the world. Those models, in turn, change how those creatures act, which changes the world. From that perspective, the question, what is it made of, becomes entangled with what do we do, knowing there is no basic stuff. Knowing that all solidity is emergent does not stop you from needing a job, loving someone, feeling pain, or making a promise. It does, however, strip away one familiar refuge: the hope that somewhere beneath all this is a simple, indestructible core that guarantees meaning without your participation. If there is no such core, meaning is not handed down. It is negotiated. It is built in the same way matter is, by repeated interactions that stabilize certain patterns. A friendship becomes real when it survives misunderstandings and distance. A value becomes real when it shapes decisions across time. A life becomes coherent when enough of its moments line up with the commitments it claims. None of that cancels the physics. The forces and fields do not care what you believe. But your beliefs, your choices, your quiet refusals and quiet acceptances are also patterns in fields. They are as physical as the chair, as the photons on your retina right now. To say that matter is not made of anything is, finally, to say that whatever you are going to be is not written into a hidden substance. It is written into the way you arrange the patterns that are possible for you. So we end in an odd place. The quest for the smallest pieces led to a view in which pieces are not fundamental. The search for what things are made of led to a view in which thing is already an approximation. The more clearly we see that, the more a different kind of question comes to the front. Not what is the world underneath, but how do we live? Knowing that underneath there may be only rules and patterns. Not a solid answer. There is no single response that physics can offer. It can only clear away one kind of illusion. The rest is up to the patterns that can ask the question. When this ends, the chair will still be under you, the room will still be there, the same fields will still be humming quietly through everything. If any of this has shifted the way you see those ordinary details, even by a little, let that shift stay. Watch how your hand rests on the armrest. Watch how your body moves when you stand up. Remember, just in the background, that none of it is made of anything in the way you first imagined. And then, in whatever you do next, treat that absence of a solid floor not as a void, but as an opening, a space where you, as one temporary pattern in a vast and restless universe, get to decide what patterns you will help sustain.